Okay, we're going to be considering shear example 2. So let's read out the question. We've got a timber beam and it's made from 200 by 50 millimeter sections and it's glued together. We've got a shear force of 10 kilonewtons. So presumably there would be a beam like there of some form with a load coming down of 20 kilonewtons, and then the shear force diagram would be 10 kilonewtons on each side, because the reaction on each side would be 10 kilonewtons. So if we did a small cut of the beam there and we had our 10 kilonewton reaction, then acting downwards there would be a 10 kilonewton shear force, and of course let's not forget that there will be a bending moment there as well. So let's sketch out the section. So we've got two sections like there, and then we've got another section like there, and both sections are the same. Let's call that dimension B1, and then let's call this dimension here D1, and then let's call this dimension here D2, and then let's call this dimension here B2. So our D2 is going to be 200 millimeters, our B2 is going to be 50 millimeters, our B1 similarly is going to be 200 millimeters, and our D1 is also going to be 50 millimeters. So let's start off with this section, with this bit here. So if that was a section of B1 and D1, and if it was bending around its own neutral axis, then we would say, well, we could work out the area A1 is going to be equal to B1 times D1, and that is going to come out as 10,000 millimeters squared. And then if we wanted to work out the second moment of inertia, so I1 would be 1 over 12 B1 D1 cubed, and that would turn out to be 2.083 times 10 to the 6 millimeters to the fourth. So that deals with the first section. Then the second bit, let's just draw it down here. So we've got a second bit down here, and it's bending around that axis there, or that would be the axis around, or that would be the neutral axis about which we would be calculating the second moment of area. So we would have A2 is equal to B2 times D2, which also works out to be 10,000 millimeters squared. And then we've got our second moment of inertia about the neutral axis, and that's going to be 1 over 12 B2 times d2 all cubed, and that's going to work out to be 33.33, recurring, times 10 to the 6 millimeters to the fourth. So that that takes us as far as working out our section properties of the individual sections. Now let's work out the position of the neutral axis of the composite section. So we could assume that just by looking at it that the composite section is going to have a neutral axis maybe around here. So just call that the neutral axis. So it's going to be bending. It's going to be bending around that axis there. So we need to work out the position of the centroid, and we're going to call that YC. So let's just say we want to calculate the centroid relative to the bottom face. So taking moments about there, we want to work out what YC is. So YC is going to be equal to A1, which is going to be the first area, and to that we're going to be multiplying that by D2, and we're going to be adding on to that D1 over 2. So we are trying to find out our neutral axis relative to that coordinate system. So our first area is going to be this A1 here, and that's going to be multiplied by this distance D2 plus D1 over 2. So if we just draw a line there, then that distance there is going to be our D2 plus D1 over 2, because that distance there is going to be D1 over 2. So we're taking moments about that line there. So we're taking moments relative to the x-axis, or around the x-axis. So the first moment is going to be A1, the area, multiplied by D2, which is the whole distance up plus half of D1 over 2, and that of course recognizes that the centroid of that section lies there. Now let's do the second bit. So that's going to be the area 2, our second area. So I'll put another shape there. So that's going to be our area 2, and our area 2, the centroid of area 2 must be acting there, and the centroid must be a distance D2 over 2 from the bottom face. So it's going to be A2 times D2 over 2. And then the whole thing needs to be divided by A1 plus A2. So we're taking moments about the x-axis, and we're considering each shape separately, and on each shape we will calculate the distance from the x-axis to the centroid of the shape. So we've done that for A1 and A2, and then we divide that by A1 plus A2, and out of there would pop our centroid. So and that's going to work out to be 162.5 millimeters. So our distance YC we've just calculated, the centroid around which is where the neutral axis is, around which the composite section is going to bend, and at which point there is going to be no longitudinal stress. In our stress distribution we've worked that out to be 162 millimeters from the bottom face, and if you'd calculated YC relative to the top face, you would get you would also get the same position. Okay, now having calculated the centroid as being 162.5 millimeters, we now need to calculate the second moment of inertia. So the second moment of inertia is going to be, I'll just call that I, and we've got to use the parallel axis theorem. So it's going to be I1 plus A1 times the distance squared that you are from the neutral axis. So in the case of the first section, which is going to be A1, we're going to want to move that distance from the centroid down to the neutral axis. So we want to find that distance. We want to find that distance there. So the easiest way to do it is work out the whole depth of the section. So the whole depth of the section is going to be D1 plus D2. So we're going to have D1 plus D2, which is going to work out to be 250 millimeters, and then from there we will subtract YC, and then from there we are going to subtract half the depth, which would be that distance there, which would be D1 over 2. So if we did that, D1 over 2, and we squared all of that, that would give us, using the parallel axis theorem, the second moment of area of the first area around the centroid. So that that squared term, or perhaps more specifically what's inside there, is going to be this distance here, so the distance of the centroid of the first area to the neutral axis. Now added onto that is going to be the I2, and that must also be A2, and that must also be multiplied by the distance of the centroid to the neutral axis. So in this case here, we've got our distance YC, and we've got that distance as the depth over 2, so we're trying to calculate that distance there, and that distance there is surely YC minus D2 over 2. So that one is a bit easier. It's YC minus D2 over 2, and that is going to be all squared. And if you work that out, that's going to come out to be 1.135 times 10 to the 8 millimeters to the fourth. So that shows you how to work out the second moment of area of the section. And in the continuation to this, we will work out how to use those values to work out the shear stress in the section.